Thank you. In the early morning hours of July 4th, 2012, before most of you were awake, history was made. It doesn't involve alien invasions or Will Smith movies, but it does involve several thousand physicists getting up early to hear an incredible announcement that a particle that we had sought for 40 years, that we had called the holy grail of modern physics, that some people call the God particle because it was so central to understanding how the universe works, or the particle that we just call the Higgs Boson, with this rather clunky name, that particle had been discovered. That next day, the headlines around the world showed lots of very happy physicists congratulating each other on the discovery of the Higgs. The whole world celebrated the discovery of the Higgs boson. Even Google got into the game. But within a couple of days, the headlines had changed a little bit to things like, well, what is a Higgs boson? Why should we care about a Higgs boson? And eventually the headlines turned more silly than serious until they actually started turning quite dark. For example, here's a Fox News headline: Higgs boson may spell doom for the universe. So how do we go in a period of a couple weeks from celebrating the discovery of a particle that no one knew what it was to thinking the world is about to end? So that's what I want to try to tell you in the next 10 minutes. And the setting for this story is actually, as Greg said earlier, the French-Swiss countryside outside the city of Geneva, Switzerland, in the shadow of the Alps. Buried under the ground there, a couple hundred feet down, is the Large Hadron Collider, a particle accelerator 17 miles around, in which beams of protons are accelerated two different directions, clockwise and counterclockwise around the accelerator, and then brought into collision. These protons are accelerated through these tubes to nearly the speed of light, like 99.999999% of the speed of light. And then, just as they get up to full speed, they're brought, two different beams of these protons are brought together in a cave we call a collision hall. The collision hall is filled with a piece of equipment we just call a detector, and in the middle of this detector, they're collided, and we take a very, very fast picture. Now, you can think of these detectors, if you want, as either the world's biggest microscopes or fastest cameras, because they have to do both. They have to take pictures of very, very small objects very, very quickly. Nanoseconds is the time frames in which we have to take these snapshots. Now, these are really incredible devices. The detectors, to me, are the coolest part of the whole thing. This is a picture of one of the two big detectors called CMS while it was under construction. This is the one that Notre Dame has played a big part in building and in understanding. It may be hard for you to see, but there's a catwalk in the middle there where there are several workers standing. When that thing was done, those two ends were brought together and closed off. It's hard to take pictures of these because they're in a cave that just barely holds them, so you can't exactly stand back. It's easier to actually look at schematics of them. This is a picture of the other detector called the Atlas detector. I just want to mostly point out that at the very bottom there are two people standing. I don't know if you can see those two figures. These are half the length of a football field and weigh in the order of 12,000 tons and cost about $250 million each to build. These are the world's largest and most advanced pieces of scientific equipment anywhere. These are the pictures they take. Here's a picture from the Atlas detector finding the Higgs boson. It may not mean much to you, but to me as a physicist, this is an amazing photograph. Here's a picture from the other detector, the CMS detector of the Higgs boson that has decayed into two beams of very energetic light. Now you might ask, and I think it's a fair question, what are we trying to learn from all this? What is studying the Higgs boson supposed to tell us? And if I had to say in one word what we're hoping to learn by studying the Higgs boson is we're hoping to learn about nothing. Well, more correctly, we're hoping to learn about nothingness. See, to physicists, it's been a long-standing problem, going back hundreds of years, trying to understand what it is you have when you remove all the stuff we're familiar with from the universe. So if we were to take everything out of this room, the chairs and carpet, the people, the air, what's left? Well, I think most of us nowadays have sort of a sense of what that is. We live in a modern era. We understand that, if we were to go out into space just beyond our atmosphere, we would get to a place where there isn't stuff. We call it the vacuum. So most of us have an image of nothingness, which is basically the vacuum of outer space, and that we live in not nothingness, we live in somethingness, because there's stuff here. But scientists have long understood that that's a very incomplete picture. For at least 100 years now, we've understood that the somethingness that we think we're made out of is actually just mostly empty space too. Just for a simple example, if I take an atom, typical picture is a proton with an electron going around it, and I were to blow it up to be about the size of a cathedral, take Notre Dame in Paris. The nucleus of that atom, the proton in the middle, would be about the size of a fruit fly. not even a housefly, fruit fly, which means that that atom is just mostly nothing. Okay? So we are basically made of empty space. We're made of nothingness. So understanding nothingness is key to understanding how our universe works. So what I want to try to do is explain to you that nothingness is a lot more complicated than you might think it is. And I want to start with an example we might all be familiar with, a bar magnet. Everybody at some point in their life has played with a bar magnet. And you know that this bar magnet has a magnetic field that surrounds the magnet. And if you've ever had a chance to put iron filings down, you can even see the magnetic field lines there. Now, you might not have thought about it in much detail, but the magnetic field just doesn't end like a couple feet away from the magnet. That magnetic field actually is infinite. It goes all the way out to the other end of the universe. It's very weak out there, but it's still there nonetheless. So these fields are filling all of that empty space. Space is filled with the magnetic fields of all the magnets in the universe. You can imagine taking all the magnets on Earth and shipping them off into deep space. We would still have a magnetic field in this room. It would be a very weak magnetic field, but it would be there nonetheless. There is nothing we can do to get rid of it. We can even destroy all the magnets in the universe. There is still a magnetic field in the room. Now, in the 1960s, a physicist named Peter Higgs proposed a new type of field, one that people hadn't really thought about before. We now call it a Higgs field. And he proposed that this is a field that fills all of space, just like the magnetic field. But instead of being like strong in some places and weak in others, this one is strong everywhere, and it's equally strong everywhere. So it's completely uniform. It surrounds us, it goes through us. The Higgs field just takes up all the universe. Now, that's an interesting idea, but how would you know if it's true? Well, I tend to think of a fish joke when I think about this. You see, there's this joke that two young fish are swimming through the water one day, and an older fish is swimming by the other direction and says to them, "Hey boys, how's the water today?" And the two fish keep swimming on, and finally one turns to the other and says, "What's water?" That's the situation we're in. We live in a Higgs field, but how do we know we're there? I mean, if it's all around us, how do we even aware of its presence? Well, when Higgs came up with the idea for the Higgs field, he actually said that, well, this actually helps explain something. For example, if we were to look at fish in the ocean, we would notice that some are capable of swimming much faster than others. The streamlined ones can go really fast. The ones that aren't so streamlined seem pretty slow as they move along. Why is that? Well, some can go through the water more easily than the others. Well, it turns out that Higgs figured out that this is the same thing for particles. Some particles move through the Higgs field really easily. It's like they're streamlined. And other particles have a hard time getting through the Higgs field. And Higgs realized that we already have a name for this. The name is mass. Things that are light, not very heavy, travel easily through the Higgs field. Things that are heavy have a hard time getting through the Higgs field. And this was what Higgs proposed mass was. That mass is nothing but how hard it is for us to get through this field that surrounds us. Now, that's a really cool idea. But in physics, cool ideas are a dime a dozen. You've actually got to figure out whether it's true. And so, as a particle physicist, when I think, how do we test this? I think, well, we've got to find some way to see if the field is really there. Now, imagine that I claimed that there was a really still pond of water right here at the front of the room, but it's so still you wouldn't be able to tell. What might you do to check? Well, I would drop something in it, right? I would look for the splash, because I can tell when I disturb it that the field is there or the water is there. Well, the same thing is true for fields in space. If we disturb them, we can see they're there. And so this is what particle physicists do. They take lots of energy, smash it together, and try to make a wave. We try to see if we can make a splash in this Higgs field. And that splash is called a Higgs boson. The thing that comes out of the water is a particle that we can actually observe, or at least we can observe it decaying. And so when I show this picture, what I'm showing you is the splash that particle physicists have made in the Higgs field. They've made this splash in that vacuum of space itself and have observed that splash. And that's what the headlines were about, that Higgs. Now, I want to end by trying to tell you about why this might spell doom for the universe, because that headline, as dark as it sounds, had some reality to it. And to explain to you why measuring the Higgs boson might spell the end of the universe, I have to say a little bit about energy and how it plays into physical systems. You see, in physical systems, you can understand a lot of what they do by thinking they're trying to minimize their energy. They're trying to get to the lowest energy state possible. So here's a simple example. Let's take a sombrero, and I want to put a marble on the top. What's it going to do? It's going to fall, right? It wants to get down to the lowest energy point it can get. So it's going to get down, it's going to end up in the rim of the hat. And what's it going to do from there? Nothing, right? it's already gotten to sort of the lowest point it can go, so it's not going any farther. Well, this is how the universe works too. Things try to get to as low as energy as possible. It turns out that the Higgs field can change its strength in order to change its energy. And so it will actually get weaker or stronger until it finds it's at its lowest possible energy. And this is the picture that we've had for a very long time of how the Higgs field would look. That is sitting at the bottom of this sort of big energy well. The problem is, once we measured the Higgs boson, we discovered that this sombrero is sitting on the edge of the Grand Canyon. Now, if I asked you again with a marble and a sombrero on the edge of the Grand Canyon, where does the marble want to be? Well, it'd like to be down at the bottom of the Grand Canyon. That's where its energy is lowest. But will it ever get there? No. Marbles can't climb the side of the sombrero. It can't dig through the sombrero. So it's just going to sit there forever in principle. Quantum mechanics doesn't work like that. And Higgs bosons obey the rules of quantum mechanics. And quantum mechanics says, in fact, the marble can tunnel right through the hat. It takes a long time. It's a very low probability event. But eventually it happens. And when it does tunnel through to the bottom of the Grand Canyon, the laws of physics change. Because all the laws of physics depend on the strength of the Higgs field. And so at the bottom of the Grand Canyon, you don't just have some difference in, oh, well, things have changed a little bit. You have a new universe. You have fundamentally changed all the laws of physics. You have basically pressed the restart button, the reset on the universe itself. Now, what does this look like? Well, it's a lot like boiling water. When you go from liquid to gas, what do? You form bubbles, right? So this is what would happen. You would actually form bubbles of a new universe inside our universe. Most of the time, these bubbles, if they're really small, would just contract back on themselves and go away. And in fact, quantum mechanics tells us that these bubbles are constantly being created in our universe. And if they're small enough, it's no problem. But eventually, you get one that's big enough, it will grow and can't be stopped. And it will grow at the speed of light, which means that by the time we see it, it'll be there. So what would this look like from the Earth's perspective? Well, it's very simple. One day, there's nothing. So, am I worried that there won't be a July 4th, 2014? Well, the nice thing is we can actually calculate the odds for this. This doesn't mean we can't work with. And you find that the odds that the universe will disappear in the next year are about 1 in 100 billion. So, am I worried? In fact, no, those are pretty good odds in our favor. But even more so, over the next decade or two, physicists are going to be spending a lot of time and effort to understand this Higgs boson even better, and in that process, understand even better what nothingness is, and find out maybe there's more surprises in store. Thank you.